Okay, in the second lecture we want to take some examples and exercise that prove that this non-empty set is a group under the binary operation, and that binary operation may be addition or multiplication. Just like if we talk about set of real number, set of rational number, set of natural number, set of whole number. So all of these the main sets, set of natural number, set of whole number, rational number, irrational number, real number, set of complex number, we will check that either these sets are group or not group. And if these sets are group, then under what binary operation and under what condition? And if these sets are not group, then what is the reason that these sets are not group? So of course these sets will be group if these sets satisfy the four axioms. The first axiom is closure property, which is also called binary operation. The second property is associative law. The third property is identity element, because every non-empty set, if that is group, should have identity. And every non-empty set under the binary operation must have an inverse. If these four axioms satisfied, then we can say that G is group. Okay, let me consider set of natural number. Okay, set of natural number under addition. What you can say? Set of natural number under addition is group, and if it is group, then we will check that either it is under multiplication is group or not group. Okay, first we check under addition. So the first property is the closure law. The closure law is for any two natural number under addition, because we are taking a binary operation over here, addition. Okay, just like I am taking two natural number 1, 2. These are two natural number. Then 1 plus 2 is equal to 3, which is again a natural number. So the first property, which is closure law, of course satisfied over here. And the second property is associative law, which is obvious, of course. Okay, because for any three element, just like 1, 2, 3 belong to set of natural number. Set of natural number 1 plus 2 plus 3 is equal to 1 plus 2 plus 3. So this is obvious. Okay, and if we talk about the additive identity, so 1 is a natural number. So is there any natural number such that we add 1 on that natural number? Is there, and there exists an element box means that there exists an element such that element in n such that when we put that number over here, either from right side and other from left side. Okay, so our answer should be 1. Our answer should be 1. Either it is those number, this box means any natural number. Okay, such that our answer should be 1. Okay, so of course if we want to get answer 1, then what does it mean by? Then it means that we will put 0 over here. Okay, but 0 does not belong to n. So what does it mean by? This means that identity does not exist over here. If identity does not exist, one property has failed, then it means that set of natural number is not group under what? Under addition, because addition over here is binary operation. So set of natural number is not group under addition. So now we are taking set of real number. Okay, set of real number under addition. We check that either it is group or not group. The first property is, of course, you know, the first property is closure property, and the closure property states that for any two real number, okay, belongs to just like if I take any two real numbers, yes, the first property is closure law. The closure law is A comma B belong to set of real number implies that A dot B mean multiplication also belong to R, which is an obvious property. Okay, the second property is associative law. As I have already described that, it is again obvious. Okay, the third property is the identity element. So identity element, the binary operation is multiplication, remember that. Okay, so if I take 2 belong to, I am taking the specific, just like 2 is a real number. Okay, 2 is a real number, so either there exists a real number, okay, such that when we multiply with that real number, our answer should be 2. Either we multiply that real number from the right side or from the left side. So yes, of course, that real number is 1. That real number is 1. So 1. Okay, so 1 is the multiplicative identity over here. Multiplicative identity. Okay, the third property has satisfied again over here, and now we check the fourth property. The fourth property is the multiplicative inverse. I am also taking not the general case, suppose, and now you can generalize it, just like here I take 2, you can take A belong to set of real number. Okay, set of real number, there exist 1 belong to R, such that set of real number A dot 1 is equal to A, which is equal to 1 dot A. 1 is the multiplicative identity. And the fourth property is for all A belong to G, there exists A prime. Okay, first I will take the specific case, just like 2 belong to set of, so there must exist, must exist a real number such that when we multiply with this real number, okay, our answer should be 1. Okay, so either it is multiply on the right side or on the left side, our answer should be 1. So of course that real number is 1/2. Okay, but suppose if I take the 0, I am taking over here 0. Okay, so when we multiply 0 with 1/2, just like 0 is a real number, so there must exist a real number, that belong to R, such that 0 multiplied by that real number, our answer should be 1, because the multiplicative inverse should be 1. Multiplicative inverse should be 1. So this is equal to, that box mean real number. Okay, so 0. So there is no such real number. We multiply, here we take what kind of that real number we take over here, our answer is 1. There is no such real number.